Yeah, there were a couple of people who submitted the homework 2, submitted the hard copy. Their graded homework is here. They are not here today. And we still have one homework 1 remaining. Your homework 2 is graded. Joshua, right? Okay. I guess we can go ahead and start. We are going to continue the discussion on the discussion we have had on chapter 3, essentially potential flow theory. We already discussed all of the elementary flows, and there were 4 of them. In our case, we had the uniform flow, we had the source or sink flow, we had the vortex flow, and we also had the doublet flow. And we learned, we understood that since the Laplacian of a stream function and velocity potential are 0 for these flows, we essentially can add them up and create more complex flows. The first complex flow we worked on was the non-lifting flow over a cylinder. Okay, the idea was you have flow that is passing over a stationary cylinder. Okay, we actually analyzed this type of flow before we became familiar with the elementary flows and their special characteristics. Okay, is there any questions about any of these topics that we covered in the previous lecture? So today we are going to expand this discussion to lifting flows, specifically lifting flow over a rotating cylinder. We mentioned this briefly in the previous lecture, but we didn't do any analysis on it. Okay, and we will continue by talking about the Kutta-Jaoukowski theorem, and that will be it for today's lecture. We'll solve some example problems too, but for the next lecture on Monday, we will go over a source panel theory, which is essentially a numerical method theory, a numerical methodology that will help you calculate lift, right? So I'll make sure to prepare a code for you to help you understand that type of theory a little better. It is really hot today. Let me take off my jacket. And your homework is also posted. That's your homework 3 is posted. It will be due Monday, March 8th. So in more than a week, probably like 12 days, right? It is due in 12 days. Right? I will add 2 questions to the homework. That is, it currently has 5 problems on it. I will add 2 questions to it to include the finite difference methodology that we covered in chapter 2, as well as the source panel theory that we will cover in this chapter. And all of the introductory, all of the tutorial that I promised will be posted this weekend. Okay. Is there any questions about the homework, about anything? No. So let's pick up where we left off. Let's talk about the lifting flow. Lifting flow over a rotating cylinder is essentially a combination of your regular flow over a cylinder plus a rotating disk. So non-lifting flow over a cylinder plus a rotating disk is going to give us flow over rotating disk. Okay. So what does this mean? We could break up this complex flow of rotating flow over a disk to simpler flows. One is the rotating disk, which is going to be similar to the vortex flow we have had, and one to another complex flow that we have already dealt with, right? So a stream function of this, I'm going to call it lifting flow over rotating disk. So LR is going to be this stream function equals to a stream function of this non-rotating flow, non-lifting, and L, for example, plus your vortex flow, right? What is the stream function? Or we can do the same thing for the velocity potential. The names are using these subscript I'm using. I'm just creating them as we go. So this refers to your non-lifting flow over cylinder. This refers to lifting flow over a rotating cylinder. Okay. So I'm going to use the stream function here. What do we have? We already have the stream function for the vortex flow. What is the stream function for the vortex flow? Go back to your notes and tell me the stream function for the vortex flow. Gamma over 2 pi natural log of R. Gamma here is the strength of your vortex. Okay. What about the stream function for this non-lifting flow? Flow over a stationary cylinder. What was this? We never calculated this. I just gave you the velocity values, VR and V theta, right? The idea was we are going to come back to this and do the calculation. So let's see how can we break the non-lifting flow over a cylinder. I think we went over it in the previous lecture that we can break this non-lifting flow over a cylinder to a uniform flow and a doublet flow. Okay, do you remember this? So essentially a lifting flow over a rotating cylinder is a combination of your uniform flow, doublet flow, and the vortex flow. So the psi of LR is going to be your psi of uniform flow, psi of doublet flow, and psi of vortex flow. You already have the psi of vortex flow. What is the psi of doublet flow? What is the sign of doublet flow? Go back to your notes. Negative kappa over 2 pi sine theta over r, right? Yeah. What about the uniform flow? V infinity r sine theta. So we have the stream function for all three. We can actually simplify the stream function for the doublet flow a little further. This length here from the center, which is essentially in your flow over the cylinder, is going to be the radius, is equals to 2 pi over, sorry, kappa over 2 pi v infinity. We can show that, but just accept it. So r is equals to the square root of this kappa over 2 pi v infinity. Okay, so let's plug all of these values in. Psi of our flow here is going to be equal to the infinity r sine of theta minus kappa over 2 pi r sine of theta over r plus gamma over 2 pi natural log of r. Let's try to simplify this a little bit. I'm going to take a v infinity r sine of theta out. So v infinity r sine of theta multiplied by 1 minus kappa over 2 pi v infinity multiplied by 1 over r squared. I just said for a doublet flow, yes. I didn't hear you. Because Muhammad is telling us, is asking whether we can, instead of replacing this non-lifting flow with a uniform flow and the doublet flow, whatever that looks, right? Instead of this, why don't we replace it with the uniform flow and the source flow, right? That's what you're telling me, right? Is this correct? Yeah. Or sink flow, whatever. So let's think about it. Why can't we do that? Or is there any condition in which we can actually, instead of using double flow, we can use the source or sink flow? How would the flow look like if we combine the uniform flow and the source flow? Yes, actually, I'm going to wait for some of you to jump in and give me some sort of an answer. Someone from these first two rows. What do you think? What do you think will happen if we combine these two flows? Just have to be able to visualize it. And just add the vectors. Some vectors are in the opposite direction. They will cancel each other out. You will get a stagnation point right somewhere. And the idea of the source flow was that a strength become smaller and smaller as you go forward, right? So you have the highest velocity here, and then as it diffuses, the velocity becomes lower and lower and lower, right? So what would you expect to see if you just combine these two flows?
I'll just take a guess that it might make like a triangle kind of shape. Like the flows would come in and then go out on the left side.
So something like this?
I was thinking the other way, but
So like this?
yeah.
Okay. Okay, so not a circle then.
I mean, not. I guess like it would be like more rounded, but yeah.
Okay. So you're agreeing with Muhammad then that we can replace this with this.
I mean, I would assume that they wouldn't flow perfectly. Like I feel like they'd go and then kind of like those ones would cut hard back.
So it will be something like this, right?
Yeah.
Irregular. Okay. That's one opinion. Who else? Who else has an opinion? First two rows. I'm going to extend it to the third. Yes.
I think. Well, I think like the first half would look like it does like in the cylinder flow, but then like once it passes, it wouldn't like go back to like a circular shape. It would go up like into the.
Exactly. And thank you. And this is something we actually discussed in the previous lecture as well. So when you add these two type of flows, think about it. Let's say we have uniform flow coming in, and then we have a source in front of it. These two velocity vectors will cancel each other out. So there will be a location where the velocity of this source is equal to the velocity of uniform flow. Then you will get a stagnation point, right? Then the next, you're going to get this essentially the same thing on the next adjacent source streamline, or adjacent to the original one, right? So essentially, you're going to get something like this, right? But as you move in this direction, your sources are not going to be completely aligned with the upcoming flow, right? They're going to be tilted. So what your upcoming flow is going to do is that it's going to change the direction of your source flow, right? So this is what you are going to see. And eventually, this source is just going to be amplified by the upcoming unit because they are in the same direction. So their velocity is going to be added to each other instead of cancelled. So this is what you are going to see, right? You will get a stream here, and then inside, your flow is going to look like this, right? So if you add a source flow to uniform flow, this is what it looks like, right? Another flow past the cylinder. That's why we need to use a doublet flow. Okay, so I just said that in the doublet flow, this is equals to your r squared. That's the radius of your non-lifting or lifting or non-rotating or rotating circle, this radius, right? If you recall, this was the doublet flow inside. And this was square root of kappa over 2 pi v infinity. So plug that in. I'm going to erase this and just replace it with r squared. We are going to have okay. So b infinity r sine of theta multiplied by 1 minus r squared over r plus gamma 2 pi natural log of r. Okay, so we have the psi for the flow past a rotating cylinder. The next step is to find the velocity distribution, Vr and V theta. Your Vr was 1 over r partial psi partial theta. Your V theta was negative partial psi partial r, right? So take the derivative with respect to theta here. This second term the vortex flow term is going to go to 0 if you take the derivative with respect to r, because there is no theta term here with respect to theta. I'm sorry. This first term, if you take the derivative with respect to theta, is going to be cosine of theta. The rest of it is going to stay the same. So we're going to get v infinity, and then r will cancel out with this r. Cosine of theta multiplied by 1 minus r squared over r squared. This r is the radius of your circle. This r is the distance from the center of your circle, right? So this is going to be capital R, and any point here is going to have this r, right? Outside of the flow. Okay, what about the theta? So let's take the derivative with respect to r here. You're going to get a negative sign. And what is the derivative of this with respect to r? To make it easier, I'm just going to multiply this by VR sine of theta, right? So we want to take the derivative of VR sine of theta minus VR V infinity sine of theta r squared divided by r plus gamma over 2 pi natural log of r. Okay, we want to take this derivative with respect to r. So let's do that. The derivative of first term with respect to r is going to be just a negative v infinity sine of theta. Okay. Derivative of the second term with respect to r is going to be, what is it going to be? The derivative of this term, v infinity sine theta r squared divided by r with respect to r. Are we all following that? What is going on here? Yes. See a couple of yeses. Okay. So what is this derivative of this term with respect to r? The numerator is essentially constant when it comes to r, right? V infinity sine of theta r squared does not change with r, right? So the only thing that is changing with r is going to be this r in the denominator. So we are taking the derivative of 1 over r with respect to r. What is the derivative of 1 over r with respect to r? Negative 1 over r squared. So essentially, you are going to get v infinity sine of theta r squared over r squared. So the negative sign comes out, cancels this negative sign. Then we have another negative sign here that will be multiplied. So eventually, you're going to get a negative sign. And then, what is the derivative of gamma over 2 pi natural log of r with respect to r? That's only the derivative of natural log of r, which is 1 over r. Gamma over 2 pi natural log of r. Again, we can take the negative v infinity sine of theta out. We are going to get 1 plus r squared over r squared minus gamma 2 pi 2 pi r. So we have VR, v infinity cosine of theta 1 minus r squared divided by r squared, and we have v theta, which is negative v infinity sine of theta 1 plus r squared divided by r squared minus gamma over 2 pi r. Is there any questions here? No? So we have the velocity distribution. We should be able to find the properties we are looking for, which is the pressure coefficient, right? But before finding a pressure coefficients, we need to have a discussion about the stagnation points. Okay. What are the stagnation points? Stagnation points are points at which velocity is 0. Okay. So we have the r is equals to the infinity cosine of theta 1 minus r squared divided by r squared, and we want it to be equal to 0, right? There are two ways this VR can be 0. Either by theta being plus minus pi over 2, or by r being equal to r. Okay? If r is equal to r, we're going to get 1 minus 1, 0, multiplied by whatever is going to be 0. If theta is pi over 2 or negative pi over 2, cosine of theta is going to be 0, and then it doesn't really matter what is your r. So for v theta, though, it's going to be a little more complex. You want v theta to be 0, so negative v infinity sine of theta 1 plus r squared divided by r squared minus gamma over 2 pi r has to be equal to 0. And we are looking for conditions where both of these velocities is 0. So for this v theta, one of these two has to be met, right? We either have to have theta is equal to pi over 2 minus pi over 2, or r has to be equal to r, because we want both velocities to be 0. Let's go with this one first. Let's analyze this one first. Okay, let's plug that in. R is equals to r. So v infinity, negative v infinity sine of theta 1 plus r squared divided by r capital R squared 1 plus 1 minus gamma 2 pi r. And this r is going to be the radius of your circle, is equals to 0, which essentially means that for r equals to r, for this condition, your theta has to be, we have v infinity sine of theta multiplied by 2 minus gamma over 2 pi r. Okay? The first thing you do is to move this part to the other side. So negative v infinity sine of theta multiplied by 2, or negative 2 v infinity sine of theta should be equal to gamma divided by 2 pi r. Then you take 2 v infinity to the other side, you get, and there's a negative sign as well, you will get sine of theta is equals to negative gamma divided by 4 pi r v infinity. Okay, do we follow this? It's just rearrangement, and you get. Eventually, for theta, if sine of theta is equals to whatever I just said, your theta has to be the inverse sine of gamma divided by 4 pi r v infinity, and there's also a negative sign. Okay, so a stagnation point. If r is equals to r, then theta has to be equals to this. R is equals to r. So a stagnation point on the surface of this rotating cylinder, which means that where r is equals to r, we have to have this condition for theta. Okay? Well, what is that value? What is that value? Do we have any constant theta here? One thing we can say is that your gamma is positive, 2 is positive, pi is positive, r is positive, v infinity is also always positive. So what does it mean for the value inside here? We have negative gamma, 4 pi r v infinity, right? So what does this mean for the value inside here? It is always negative. The value inside the inverse sign is always negative, okay? Which essentially means that your sine of theta is always smaller than 0, okay? If r is equals to r on your surface. Does this make sense? Do you follow? A positive value minus a positive value is always negative value, right? Essentially, your sine of this theta is always a negative value. So where your theta starts from here, right? This was the sine convention. This was your r. So where is going to be your theta located if the sine of that theta is always negative, right? If you start theta from 0, sine of 0 is 0, then sine of the, what is sine of 30 degrees? Who remembers what is sine of 30 degrees? Was half, right? It's a positive value. That's the point. So you start with a positive value, then you go to sine of pi over 2, which is positive again, and then you'll start decreasing to 0. So this part is always positive, which essentially means that your theta has to be in the third and fourth quadrants, or the fourth, in the third or the fourth quadrant, for this to be true, for the value of sine of theta to be a negative value. So what does this tell us? This tells us that the location of the stagnation points are in the bottom half of your circle. Does it make sense? Okay. So let's investigate there. Let's say your gamma, let's talk about a case where your gamma is smaller than 4 pi r v infinity. What can we say about the value inside this parenthesis? It is going to be always smaller than 1, okay? This essentially means that we will have a value of sine of whatever theta that is negative something between 0 and 1, right? Which is telling us that we are going to have 2 solutions, right? Because let's actually do this. Let's say sine of a theta is 1/2, right? And we want to find theta. What is this theta? Negative 1/2. Sine of a random arbitrary theta is 1/2. What is that theta? This value, right? 30 degrees. So negative 30 degrees, essentially, right? This is 1. Is this the only value? Is this the only true solution, though? Is there any other solutions to this problem? 180 plus 30 as well, right? So essentially 210 or negative 150. So there are 2 solutions. If your gamma is smaller than 4 pi r v infinity, you are going to have 2 solutions for this problem. What does this mean? This means that you are going to have 2 stagnation points on the surface of the circle. So your flow is going to look like this. stagnation point, right? Which was the original drawing I had for this type of flow, rotating flow over cylinder, right? But what if gamma is equals to 4 pi r v infinity? What is the value we're going to get here inside this parenthesis? -1, okay? What is that theta that's going to give you, the sign of that theta is -1. Sign of what theta is -1? -pi/2, right? Or 3 pi over 2, right? So if your gamma, first condition, gamma was smaller than 4 pi r squared, this is how the flow would look like. Second condition, gamma is equals to 4 pi r v infinity, your flow you will only have one stagnation point. So your flow is going to look like this. Okay. What about the third case? Third case, sorry. Third case is when gamma is larger than 4 pi r v infinity. What does this mean for whatever that is inside this parenthesis? Bigger than 1, okay? What is the theta for? What is the theta for? There is no theta, right? Sine is always between 1 and -1, right? So if this was the case, what does this mean? This essentially means that, how did we get to this solution? We assume the stagnation point is on the surface, okay? So if that's the case, then the stagnation point is not on the surface, and R is not going to be equal to R. What does this mean? Going back to your VR, what was VR? It was V infinity cosine theta, right? 1 minus R squared over R, right? We want this to be 0. There were two conditions. Either R is equal to 1, R, or theta is positive and negative pi over 2, right? So when R cannot be equal to R, then we can safely conclude that your theta is positive and negative pi over 2. And since we want V theta to be 0, this time we plug, instead of plugging in R equals to R, we are going to plug pi is equals to, theta is equal to pi over 2, right? What is the sign of pi over 2? 1. What is the sign of negative pi over 2? -1, right? So this essentially means that we are going to get two solutions, again, two stagnation points. Both of them are going to have, one of them is going to have positive pi over 2, the other one is going to have negative pi over 2 for theta, okay? And if you plug in the value, you can calculate the R here. I'm just going to go back to my notes and write the value here. R is going to be equal to gamma divided by 4 pi v infinity plus minus. It comes from this plus minus, right? Because you're going to get plus minus 1 here. A square root of gamma squared divided by 4 pi v infinity squared. Again, yeah, yes, minus R squared. And this is whole square root. You get a polynomial function, and these are the roots for that function. Okay, So for theta is equals to pi over 2 negative pi over 2, we are going to get two r's. One of them is always going to be smaller. If you do the negative sign, your r is going to be always smaller than your radius of the circle. So what does this mean? And the other one is going to be always bigger. So your stagnation points, your mathematical stagnation points are going to be one inside the circle on pi over 2 line and one outside, right? This is an illogical, irrational solution because there is no flow inside the circle, right? So we can just dump this solution and get the new stagnation point. So a stagnation point for the third condition is not going to be on the surface, of the cylinder. So this value of the strength of the vortex is going to be very important here, very crucial here in determining where the stagnation points are. Okay, which essentially going to it is going to tell us that the value of the vortex strength, which is essentially the same value as the circulation we saw in the previous chapters, right, is important in calculations of pressure coefficient as well as the lift coefficient. Do you guys have any questions? That's right. So for vortex flow, you have gamma, which is circulation, the strength of the vortex, right? We have seen circulation before, right? And we also have lambda for the strength of source or sink, right? We also have kappa for the doublet flow. Well, for kappa, you can always use the formula I gave you, right? Your R squared is kappa divided by 2 pi v infinity. Right, so you don't need to use kappa, you can just replace it with that. And this is what we did here, right? Because we had a doublet flow. Okay. Okay. So let's move on. Let's find the pressure coefficient on the surface of this rotating disk, right? Because we want to find the lift and drag, right? And the only way to find the lift and drag in an inviscid flow calculation was to find the pressure coefficient. What was the definition of pressure coefficient? P, the local pressure at each point, minus P infinity divided by Q infinity. We actually showed in the previous lecture that this is equals to 1 minus V, your local velocity divided by V infinity squared. Okay? And V infinity on the surface is VR ER plus V theta E theta, right? But for VR, I don't know if I remember it correctly, but it was V infinity cosine of theta 1 minus R squared, right? So on the surface, this VR is always 0 on the surface of the cylinder because your R is going to be capital R, right? So this part is 0. We are going to have V infinity is equals to V theta. So your pressure coefficient is going to be equals to 1 minus negative V infinity sine of theta 1 plus R squared over R squared minus gamma 2 pi R divided by V infinity. Okay? to the power 2. Yeah. We can essentially take this to the second power, raise it to the second power, and eventually get this final value, 4 sine squared of theta plus 2 gamma sine of theta divided by pi r the infinity plus gamma over 2 pi r the infinity squared for Cp. So we have the pressure coefficient as a function of the strength of your vortex and theta, the location on the surface. We essentially have the distribution or the distribution of pressure coefficient on the surface. How can we use this and find the lift coefficient or drag coefficient? Who can tell me? Who can answer that question? How can we use pressure coefficient and find the lift and drag coefficient? What was the formula? It will be integral of what? 1 over c, right? Integral of 0 to c dx for lift, right? And for drag, we're going to have 1 over c integral leading edge to trailing edge. Same thing, it's just different body. CPU, CPL, dy. Okay, these are the formula. And this is actually where you get another bonus if you plug in this value. The idea is you use this pressure coefficient distribution and calculate the lift and drag coefficient using those formula, right? Does this make sense? Okay, you get a bonus for it if you do so. So I'm not going to do the calculation here, but this is the type of calculation I would encourage you to do, because the integral of sine squared is something you may see in an exam. So you can definitely write it in a cheat sheet, bring it with you, but it's not a bad idea to have some sort of practice with. Okay, so if you can work on this calculation, the integral of CPU to get the final Cp. But eventually, what you're going to get for Cl is going to be gamma divided by r v infinity, and your drag coefficient is going to be 0, right? What does this mean? This means that for a rotating disk, because of the pressure difference on top and the bottom, you're going to get lower pressure on top and higher pressure. This is supposed to be lower pressure and higher pressure on the bottom. You are going to lift up. Okay, but the drag is again going to be 0, which we said this is called the D'Alembert D'Alembert paradox. The guy's name was D'Alembert, a French, I think, physicist. Yeah, because drag is obviously not 0. We are pushing this cycle back, but we calculate the drag to be 0. Okay. Is there any questions so far? Yes. No, 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 no. As long as you have an accurate description of pressure distribution, your CL calculation is accurate, right? Because lift is mostly a function of pressure. The reason we're gonna get lift, as Paul asked in the previous class, actually, is because of friction, right? So, in like from a physical perspective, if we don't have friction, we wouldn't have lift, right? But the amount of lift is due to the pressure difference on top and the bottom. As long as you can calculate the pressure difference on top and the bottom, you should be able to get the lift coefficient. But here, since we are the most of the drag is due to the friction, is a friction drag, and we are neglecting friction, we are essentially not seeing. That no, and we're gonna do that right now, actually. The point is the contributions of friction to the lift is going to be very minimal. Okay, that's the idea. So even if you include friction, the contribution will be very minimal. Okay, so let's try to find lift using this. If you recall, we defined this force coefficient in general as force divided by Q infinity S, right? We are dealing with lift, so we're gonna do, and it's a two-dimensional thing. So we're gonna do L prime, lift per unit span, and Q infinity S. Okay. And S here, you're dealing with lift per unit span, so your S is R, only R. And we also have another formula for CL, which came from there. Gamma R V infinity, right? So your L prime can be Q infinity R multiplied by your CL, which is gamma R V infinity. These two will cancel each other out. Q infinity is your dynamic pressure, 1/2 rho V infinity squared, and this is actually 2R, right? Because that's going to be the radius of your, the diameter of your circle. And Q infinity is 1/2 rho V infinity squared. Plug all of these in. After you cancel whatever you can cancel, your lift is going to be equal to rho V infinity gamma. Lift per unit span. So for two-dimensional case, you can calculate lift per unit span. And this is a very important conclusion in aerodynamics. This is called the Kutta Jaoukowski theorem. This theory is telling you that your lift is a function of the circulation around that cylinder. And we can actually expand this to the other type as well. We can actually say that the lift is going to be a function of circulation in general. For this case, for the rotating this around the cylinder, this will be your equation. But in general, lift is going to be a function of the circulation. And based on this theorem, we are going to develop the thin airfoil theory in chapter 4. Okay. Is there any questions so far? No? So it is all clear? Okay. So let's solve an example then. The example is telling us to consider And this is, think of this as a pop quiz. So I want you to work on this and give me an answer and submit your answers. The example is telling us to consider the lifting flow over a circular cylinder. So lifting flow over a circular cylinder, which means that we are dealing with this type of flow. Rotating cylinder, lifting flow. The lift coefficient is 5, number 5. You want to calculate the peak negative pressure coefficient. So let me write it on the board here. Lifting flow, CL is 5. What is the peak or the most negative pressure coefficient? Most negative. I assume you can say that the minimum pressure coefficient. But yeah. So let's do that. The lifting flow. So flow over a rotating cylinder. Whenever you hear lifting flow over a cylinder, it is flow over a rotating cylinder. Right? But the other type of flow was non-lifting over a cylinder. You got to do the calculation. I'm just going to do my. Sure, hold on. You're going to have like a couple more minutes. Let's do 4 minutes. And then let's actually add to this problem. So you want to find the most negative CP. You also want to find the location of the stagnation points. Location of stagnation points. Then understand there, where the pressure equals the free stream static pressure. But location of stagnation points in general. How can you find the location of a stagnation? Okay. Okay. Do you have anyone? Do we have any solutions? Yes. You have the solution. Okay. So inverse sine of -5/4 pi. That's correct. That's correct. So whoever can give me, I'm gonna play this video for you, right? And you have still time to essentially solve all three. Whoever can solve all of this before I solve it for you and submit it to me, they give it to me before like I solve it. They'll get a bonus point for each section. But I'm gonna play this video. If you want to watch the video, you can watch the video. If not, you can. It really depends on you. So the flow over a lifting cylinder. Let me see if we can turn down the lights a bit. Flow over the lifting cylinder. No. Flow over lifting cylinder, as we said, just the rotation of the cylinder is going to cause the generation of lift, right? We analyzed the non-rotating cylinder flow over non. We saw there was no lift, but when we started rotating the cylinder, we got some lift. This effect is called the Magnus effect, and it's actually a very interesting effect. So there's this guy who is going to give us some ideas on.
Yeah, me too.
Right. Let me see.
These rubber bands, and we're going to rubber bands, and I'll meet you at the table service. Okay, for this levitation, we're going to use air pressure. Now, you've heard me use air pressure before.
I'm sorry, I have to.
Use it to make objects hover in the air. But today, I'm going to show you how to manipulate it to create what's called the Magnus effect. No, not magnets. Magnus effect.
Magnus.
But before we get into it, let me show you a little experiment. This is a magic soda can. No, just kidding. It's just a regular can, okay? It's empty. But right now, when I set it on the table, gravity's holding it down, but we have equal air pressure on this side, and even inside, because it's open. It's equal on all sides, which is why it's sitting still. But I'm going to blow air on one side of this can. What that's going to do is faster moving air will create low air pressure. Now, what that means is there'll be low air pressure on one side and high air pressure on the other side. So guess what happens? The can will be pushed into that low air pressure pocket. So if I blow on it on this side, you're going to see the can move that way.
That's the idea of the lift, right?
Did you see that? I'll show you again in slow motion. It's actually moving towards the low air pressure pocket. Let me magnify the effect with a second can. If I blow down the center of these two cans, the low air pressure pocket on this side and the high air pressure over here will push this can this way. Just as much as there'll be low air pressure pocket here, and there'll be high air pressure pocket here. So if I blow air here, this one will move this way. So instead of being pushed apart, they're going to connect. Perfect. They connect, not magic, science. Now, imagine if there was faster moving air on this side and slower moving air on this side. Well, that means there'll be lower pressure here and higher pressure here. Now imagine it being turned sideways. Finding the faster moving air on top and higher pressure on the bottom, we can create lift. So how are we going to do that? We're going to take advantage of the shape. See, we're going to get this spinning in the air like this. Now what that's going to do is if this object is moving through the air and it's spinning this way, well, this rotation is helping the air over the top. It's assisting it move faster, just as much as it's slowing the air on the bottom. You'd have low air pressure on top. You'd have higher pressure on the bottom. That creates lift, and that gives us the Magnus effect. So let's turn that into an airplane. Seriously. All you need for this one are 2 cups. Oh, okay, I'm just kidding. You need 2 cups. We're going to need 4 rubber bands, and we're going to need some tape. Now, it's very easy to make. We'll just place the cups base together, and we're going to place some tape all the way around it. So I'm just placing the tape right down the center. We don't want it to be loose. We want it to be pretty secure because it's going to be spinning. We don't want it to fall apart. Now we're going to take these rubber bands and we're going to interlock them with each other. And we're going to create one long elastic like rope. Now I'm using 4 rubber bands, but you could use 5. Probably need more than 3. 3 would probably be the low end. And now what we're going to do is we're going to take this stretchy rope and we're going to wrap it around this. Now the way I'm going to wrap it is so that you spin it around just on the base like this, nice and tight, and stretch it out like this. Now what's going to happen when I pull this back and shoot it like a slingshot? What's really happening is it's going to uncoil through that rubber band, which gets it spinning. But it's also shooting forward because we just shot it like a slingshot. You're going to have the cups rotating like this, creating low air pressure on the top, high air pressure on the bottom, and we create lift. That's right, these cups are going to act like a paper airplane. The faster you get it spinning, the more lift you'll create, like that. You should probably do this outside. I'll take this outside. All right, finish up.
See, you see the generation of lift, it goes up.
Pretty cool, right? I hope you enjoyed this episode of Impossible Science. If you did, let me know by smashing that like button.
Yeah, can go ahead and smash the like button later. But let's actually, there is another bonus point in this class. We had a lot of bonuses in this class, so make sure to, I guess, use the bonus point. If you use the Magnus effect to create some sort of an airplane, something that resembles an airplane, you will get 2 bonus points. Okay? You either take a recording of it, send it to me, or just bring it in class, test it. It shouldn't take more than a couple of minutes, right? I guess to give you a little more practical understanding of lift. Does it make sense? Pardon me? That's the idea. Something that works based on the principles of Magnus effect, rotating cylinder. It's like something as simple as these cups, right? As long as you can get it go up in the air a little. But however you can rotate it, right? Okay. And you will get 2 bonus points. There is one comment here. You want us to email? Yes, if you are watching this online and you want to get the bonus points, you have to email me the answers, I guess, right away, because we have to get to work on the solutions right now. Okay. Is there anyone who has the answers? Okay. Who, just show of hand, who has the answers? No. We are looking for a theta here. But first 2, let's do first 2. Who has the answer for first 2? 1 person, just 1, 2 person, 2 people, 3, 4, just 4. I'm gonna trust you guys. You get the bonus points, and just remind me after the class. Send me an email, okay? And it was a loss for whoever didn't raise their hands. It always works based on trust here. Okay, so the first part is asking us to, the first question is asking us to find the peak negative pressure coefficient. Which question were you asking? Part 3 or part 2? You asked a question about in terms of pressure, right? What did you ask? Then for first part, yeah, the most negative CP, yeah. But for second part, I wanted you to find the location of the stagnation points. So essentially R and theta, and location of where P equals to P infinity. Okay, so let's do this. The idea is we have CL is equals to 5, right? So we have V theta. Let's actually do CL first. CL is gamma over R V infinity. So your gamma is going to be equal to R V infinity 5 R V infinity, right? What do we want to find? We want to find most negative CP. So CP minus V infinity square, right? Can actually rewrite this as a function of V infinity. Okay, do we have the velocity? Velocity. What is the velocity? What was the equation for velocity we have had? It is on the surface, so we only have V theta, right? What was the formula for V theta? It was negative V infinity. I don't remember the formula. Sine of theta 1 plus R over R squared, right? Minus gamma over 2 pi R, right? And we are looking for this value of CP, most negative CP, on the surface. So R is R. We're going to get 2 here. What are we going to get here? So V theta is going to be equals to negative V infinity, negative 2 V infinity sine of theta minus gamma divided by 2 pi R. Okay, just plug gamma in. V theta is going to be equal to negative 2 V theta sine of theta V infinity, sorry. V infinity sine theta, and then we have 5R V infinity divided by 2 pi R. 2 R's will cancel out. We're going to get 2 V infinity sine of theta minus 5 over 2 pi V infinity. Okay. How can we simplify this further? Or can we simplify this further? What can you say about theta? 0? Theta is going to be at the top and bottom. So pi over 2, right? That will be the location of your most negative, essentially at the bottom. So at negative pi over 2. So we're going to get negative 1. V theta is going to be 2 V infinity minus 5 V infinity over 2 pi. Okay, plug that in to get the location of the most negative. Peak negative. V infinity is going to be 1 minus 2 V infinity minus, we can take the V infinity out, 2 minus 5 over 2 pi V infinity divided by V infinity squared. The infinities cancel out. Your CP is going to be equal to 1 minus 4 to the power 4, and then minus 20 divided by 2 pi plus 25 divided by 4 pi squared. And let me see if we have the final value for it. For pi, you can just plug in 3.14, 3.14. And eventually what you're going to get is going to be negative 6.82. Okay. Well, how can we solve that? Yes. stagnation velocity. A stagnation velocity is 0. I didn't use a stagnation velocity. The idea was, I said that the peak, this most negative pressure happens at negative pi over 2. So for theta, I just put pi over 2. Okay. Yes. That's the idea. If you go back to the non-lifting flow, we actually we showed if you recall, we had this function that went from -1 to -3, right? You remember this? That last class, yeah. Sure. Yeah. So you can actually prove that you're going to get the most negative value, which does make sense because you are generating lift in that direction, right? So you're going to get that. Yes. At the bottom of the rotating circle, yeah. What comes out at 1? That's 1, yep. Yeah. That's, you can actually, you didn't need to put sine of pi equals to over 2. You can just plug in this function here in CP and get the most negative value based on different thetas. That would have given you pi equals to theta equals to negative pi over 2 as well. I don't know if that answered Jacob's question though. We are already out of time. So we are going to come back to these 2 examples. I think I need to solve the first example again because I see some confused faces. That's all right. We are going to go over the first example again. We're going to solve the 3 examples on Monday, and then we are going to do the source panel theory, which is a numerical method. We solve some examples for those numerical methods. Your homework is uploaded. Just make sure to, not all of the questions are uploaded. I will add 2 more questions to the homework by Monday. And yeah, there are 2 bonuses. One was a derivation. I don't remember what derivation it was. I guess the derivation of CL and CD, right, for the lifting flows, right? And then the other bonus is 2 bonus if you can use the Magnus effect to create a lifting cups would work fine, as you saw in the video, right? Okay. If there's no other question, then that's it. Have a wonderful weekend. There's no classes tomorrow, so I assume you're gonna start your weekend early. And
did you want these quizzes?
Yes. Please submit the quizzes. This will be counted as your attendance. And there are 4 people who raised their hands. Just send me an email. I know the name of just one of those. 2 of the 4 people. No. Don't tell me. Sure.